Okay, so this is the video for section 2.7 of Unit 2, VSEPR and hybridization. Now, I didn't do a video for 2.6 because there were no practice problems, and I'm confident that my AP class can annotate. So, skip the 2.6 intentionally. Okay. Let's see what's going on here. We learned this last year too with my honors class. Okay, so let's see. Starts off by talking about shapes. Okay. So depending on how things are bonded, they will have a certain angle. Like CO2, carbon dioxide. Like here, what they're talking about CO2, carbon dioxide. It's like a carbon double bonded to an oxygen double bonded to an oxygen. So this angle right here it's a 180-degree angle because it's two double bonds. So these are very, very rigid and straight bonds, right? And so this is an example of SO2, right? But then SO2 has this lone pair here. So this is 120, this is 120, and this is 120. And so from the top it looks like this, like an aerial view. It kind of looks like a Mercedes-Benz logo. You know what I mean? Like a peace sign. But from the side you can see that it's boom, 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 right? To understand and predict molecular geometry, aka the shape, we usually use a combination of ideas that form the valence shell electron pair repulsion, the VSEPR theory. This is very important. I gave you guys a document last year that had all the different angles and shapes of all the VSEPR orbitals, right? So this is how we identify the type of hybrid molecular orbitals that are forming, where we allocate the electron pairs between bonding and pairs and lone pairs, and the consideration of Coulomb's law to ensure minimal repulsion. So, for example, I believe this is XeF4, xenon with 4 fluorides. And so this is what it basically looks like. Each one of these are bonded equally and the same. It's the same atom, all 4 sides. So, they all have the same electronegativity, they have the same mass, they have the same everything. And so there are 4 things that are bonded, and there are 2 lone pairs. So here is, let's say this is a fluorine. This is a fluorine. This is a fluorine. And this is a fluorine. And here you have the 2 lone pairs. Now, if you look at it from the top, this is what it would look like, right? You would see the 2 lone pairs here, but then you would have the fluorine here, 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 and here. Okay, so 6 orbitals will arrange themselves octahedrally to minimize repulsions, right? Because all these things, they're not attracted to each other. It's not like there's a positive charge and a negative charge, and then they want to be attracted. They want to all stay as far away from each other as possible. However, the lone pairs are more strongly repulsive, so they'll occupy positions further away. So as you can see, as I drew here, you can see it here. The lone pairs are up here and here. They are the furthest away from each other. You're not going to find a lone pair here. That's not going to happen. Okay, so let's keep going. No, it's a lot of pages in this section. Oops. Okay. Okay, we know a lot of this already. Most of the atoms that get involved with covalent molecules from the second period of the periodic table, such as carbon, nitrogen, oxygen, some of the more popular elements, normally make use of S and P orbitals to form sp, sp2, and sp3 hybrid orbitals. Then they establish the initial arrangement of electron pairs. So when you have an s orbital, it's like this. It's like a circle. But when you have, let me see if they show it. Yeah, when you have p orbitals, it's like one is here, one is here, one is, so that's like, let's say, the y axis, right? Then you have one here, and the x axis, right? And then you have one that's coming out the page, right? And that's the z-axis, right? So it's three-dimensional if you think about it, right? You have one go up and down, side to side, one like kind of coming at you. Okay, so this is a methane molecule that is tetrahedral. Tetrahedral. So it's like a pyramid almost, you know? So if you have this, 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 and this, right? If you connect it right here, what does it look like? It looks like a pyramid, right? And so it's just like that. It's just like the pyramids of Egypt, right? And so each one of these angles here is the same. It's 109.5. And they're all equal repulsions. And the goal here, since it's, think about it, it's repulsions. They want to be the furthest amount of space away from each other. The maximum distance is 109.5, and that's where we get that. Okay, this is a little bit different. This molecule also has the pyramidal shape, right? So it has this boom, 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 right? But the stronger repulsion of the lone pair, so these guys are a little bit stronger, right? And they push things a little bit more away. So this is, instead of it being 109, it's 107. Okay, and then a water molecule is bent. So now this oxygen is a lot more electronegative. Look at its entire, like, you know, its field is huge. So this creates a bond angle of like 104.5 between these two guys, 104.5. So those are sp3 orbitals. Now sp2 orbitals, and look, oh, this is what I was kind of drawing. Like, this is the s, right? This is an s orbital. This is the first two, like 1s2, 2s2 that we talked about in electron configuration. And three orbitals will take up positions 120 degrees away from each other to minimize repulsions. This forms a trigonal planar. So this is what they're talking about, trigonal planar. Boom, boom, boom. And you can look at it like a pie, right? If you cut it into three pieces, it's a total of 360, right? Divided by 3, they're all equal, right? Because if it's, hopefully, it's at least here and here, how they're showing it, it's the same element here, right? So it's 120 degrees. So this is 120 degrees. This is 120 degrees. And this is 120 degrees. So that adds up to 360. All right, let me see. Okay, this is trigonal planar, right? And then it becomes tetrahedral. When it adds this fluorine here, it becomes this and this, right? The resulting Bf4 minus ion will be tetrahedral in shape and will have 4 bonding pairs. And remember, they're all going to be equal. And I believe this one is 109 for each of these. 109. On this side, between this one and this one, that's also 109. This one and this one is 109. Everything is 109 degrees. Okay. But this is different. There's a lone pair here, and the lone pair has a little bit stronger. And remember, that makes the 109 turn to a 107.3. Right? But here they're showing you 109, but guess what? It's 109 here, 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 109 everywhere. You can knock this over, it'll be all the same. It'll look exactly like this, no matter how you knock it over. Other times, a half-filled p orbital can be used to form something called a pi bond, as the second bond is a double bond. Okay, so here they're showing you when you double bond, right, it forms a pi bond, a pi bond, a pi bond, a pi bond. And a pi bond is formed by sp2s overlap. Notice that the original geometry trigonal planar and the molecular geometry trigonal planar are unaffected by the formation of the pi bond. Only bonding pairs in pi bonds and lone pairs determine the orbital geometry. So 3 bonding pairs in a pi bond. Orbital geometry is trigonal planar. Molecular geometry is trigonal planar. Okay. But 1 bonding pair in a pi bond, the greater repulsion of the lone pairs on the oxygen pushes the hydrogen closer together. Oh, that's like for H2O, where there's 1 bonding pair in the pi bond, and the rest are the hydrogens. Two bonding pairs in a pi bond and a sigma bond, and 1 lone pair. So here we have 2 bonding pairs, 2 bonding pairs, and 1 lone pair. And so that, this angle is 120, this angle is 120, and this angle is 120. And this is called bent. Okay. When you have 1 bonding pair in a pi bond, I guess they're not showing us an example here. 1 bonding pair in a pi bond, they don't have an example. Okay, so let's see what this kind of looks like when you have a s and a p orbital hybridized to sp hybrid orbitals. Okay, and there's not many examples of atoms that have 2 valence electrons, group 2 metals, but form covalent bonds, but BeCl2 is a good example where both the orbital geometry and the molecular geometry are linear. Okay, and in acetylene or ethene, each carbon only needs to form 2 pi bonds because it's double bonded to the carbons. There's a bond here, there's a bond here. 2 sigma bonds, so forms a sp hybrid orbitals. And again, the original geometry and the molecular geometry are linear. Again, the formation of the second and third pi bonds in the triple bond has no effect on the geometry. Only bonding pairs in sigma bonds and lone pairs determine the orbital geometry. The Lewis diagram for CO2, which we talked about earlier, and this is a great Lewis diagram, shows that there will be 2 sigma bonds. So 2 sp hybrid orbitals needed, leaving 2 unused p orbitals to form the pi bonds. Each oxygen will form one sigma bond and have 2 lone pairs, so 3 sp2 hybrid orbitals needed, leaving 1 unused p orbital to form the pi bond. Okay, so we have a pi bond here. With 1 pair, we have a pi bond here. Right, so these are sp and these are sp2, but they're double bonds. So one will be sp, one will be sp2. The sp hybrid orbitals make the geometry linear, and the sideways overlapping of p orbitals to form the double bonds has no effect. Excuse me. Okay, here we go. Here's a good chart. So if there are 2 sp hybrids, and so this is sp and this is sp, this is a 180-degree angle, straight line. It's linear, and that makes it linear. If there are 3 sp2 hybrids, that means it'll all be equal, like the Benz logo that we talked about earlier, and each one will be 120, and that's called trigonal planar. Why they wrote planar trigonal, I don't know. And then if it's like a pyramid, where it's like boom, 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 with one in the back like that, and so it comes out like, right, each one of them angles are 109.5, and that's called tetrahedral. So all angles are 180 here, all angles are 120 here, and all angles are 109 here. Again, you have 2 sigma bonds, you will be linear. If you have 3 bonds that are equal, it'll be trigonal planar, like the Benz logo. We have an example of that here. I'm surprised that they use a double bonded oxygen. sp2 is also if it is bent, if there's a lone pair here. And then remember, these would be 107. And that leads to 1 lone pair and 1 sigma bond. And then tetrahedral, if you have 4, they're all equal, then they're 109. Remember that. And then here it would be a little bit different because there's 1 lone pair, and here it would be different because there's 2 lone pairs. And then here's 5 and 6. I don't need to review this. You guys should use this as a reference. I'll also give you another reference. We may need to have to come back to these based on the questions. Okay, let's see here. Let's talk about bond length. So summary of bond properties, bond length. As we decrease, as we move from single bonds to double bonds to triple bonds, it gets smaller. And we talked about this in class. If you're holding hands, just one hand with someone, you're going to be pretty close to them. When you hold 2 hands with someone, you'll notice that your bodies are closer. If it was possible for you to hold 3 hands with someone, you will notice that you were even closer. These are angstroms. Just another way to measure really small things, angstroms. All right. And then it'll also increase the atomic radii of atoms. So here we have a single bond, and as we increase, right, our size of our molecule, the element here, we will also increase the size of the radii. Here, now this talks about bond energy. Bond energy will increase as we move from single bonds to double bonds to triple bonds. That makes sense. The more bonds, the stronger the bond, aka, what do they call it? Bond energy. Okay, and then bond angles, as we increase from sp3 to sp2 to sp, we see these angles. They're all the same, but the angles increase, right? Become wider and wider because there's less. And if they're repulsive, right? There's more space here to be repulsive. Okay. And so bond dipoles and molecular dipoles, you have to kind of see, where these the dipole moment is going. You have to be cognizant. Remember, wherever it says plus, that atom is more, usually like a positive charge, but more so if it shows like this, right? The arrow is showing whether it is more electronegative, and you'll notice that chlorine, oxygen, nitrogen, chlorine, that's where the arrow is pointing. Fluorine, always fluorine, right? Okay, let's get started with some questions. Okay, question number 1. Which bond has an angle of that's closest to 120? So it can't be this. We know this is 180. Can't be this. This is 90. I would say it's this. This is a bond that's closest to 120. It's definitely not this. There's a lot going on here, so I wouldn't say it's this. I would say it's C. Moving on. Molecule 1, 2, 3. Lewis diagrams of molecules of 3 different hydrocarbons shown above. Which of the following claims about the molecules is best supported by the diagrams? All the molecules in one lie on are in one plane. That's hard to say. If there were double and triple bonds, that would be easier to say. All the molecules have the same empirical formula. Not true, because there's 1, 2, 3, 4 empirical formula. Let's see, there's 3 carbons to 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens, 3 carbons off the bat. No, 1, 2, 3, 4, 5, 6. 6 hydrogens, and then 1, 2, 3, 3 carbons, and 4 is it? 4 hydrogens. These are not empirical formulas, so it's not A, it's not B. The carbon-carbon-carbon triple bonded angle in molecule 2 is close to 180. I would say this is the right answer. It's got to be, right? Because if it's a double, now if you remember, I just showed you this earlier. This is a double bond and a double bond, right? And if they're saying this is a 180-degree angle, why would this carbon not be also 180 degrees? So I'm picking this. The strongest carbon-to-carbon bond occurs in molecule 3. That could also be the answer. So you should pick the best answer. Best supported by the diagram. The strongest carbon-to-carbon bond. So this is technically true. The carbon-carbon-carbon bond is close. Is it close to 180 or is it 180? I would say it is 180. But the strongest carbon-to-carbon bond occurs. Well, these carbons are just single bonded, and these are double bonded here. And then regular bond. But the strongest carbon-to-carbon, this is undeniably the right answer. The strongest carbon-to-carbon occurs. So yeah, that is true. D is undeniably true. You can't deny that. So that was a good answer. I guess C was a good answer, but D is a better answer. And I guess you'll get questions like that on the exam. Which of the following diagrams experiments are represented by X and Z? Which form molecular... Which of the following diagrams, elements are represented by X and Z, which form molecular compounds with one another. Okay, so they're more formal. Which diagram represents a molecule that has been that has a bent molecular geometry. Okay, so really quickly, just in case I don't want to get it wrong, a bent, I believe, just has the one lone pair, just to be sure. I believe we're on page 9. Once we're done. None of these are obviously bent. Okay, so bent is when you have like water and there's two lone pairs and two bonded atoms. So let's go back here. No, not here. Here. Well, that's a lot of questions. Okay, so there should be two lone pairs and then two things attached. So I would say this one is bent because this one has the two attachments here, right? One, two, and then it has one lone pair here, and then it has one lone pair here. Okay, all right. The geometry of SO3 is best described as, so really quickly, let's look at a periodic table. S would normally have 6 valence electrons, right? Because it's in group 16. And then, okay, so S is here. 1, 2, 3, 4, 5, 6. And then I get an oxygen. That's a negative charge. There's an oxygen, and then a negative charge, and there's an oxygen with a negative charge. And so there's probably a double bond here because SO3, the oxygens don't usually, just bond once. So I think what you would get is a double bond with this oxygen, a double bond with this oxygen, and a double bond with this oxygen. But you would also get, so it's 1, 2, 3, 4, 5, 6 that are being shared. So I guess this would, since there's no lone pairs, this would be like the Benz logo. I don't know. I just keep, you can call it the peace logo too, I guess. But maybe this is my materialism coming out. So this angle would be 120 degrees. This angle would be 120 degrees. And this angle would be 120 degrees. And I'm pretty sure that it's called trigonal planar because it's 3, right? And it's on a plane. And what I mean by on a plane, I don't mean like, like a plane like, right? I mean like on a plane, like a flat surface. And on this flat surface, you are putting this plane, and then on here, you are cutting like a pizza. You are cutting it in 3 pieces. And so each angle here will be, on a flat surface. Because if it wasn't, then the angles if it's 3-dimensional, that's more like pyramidal, right? It would be different. Okay. Question number 5. The Lewis dot diagrams for CO2 and SO2 are given above. The molecular geometry and the polarity of the two substances are. Now, so this would be definitely like this and like this. And so here also it would be like this and like this, pointing this way, and this would be like obviously the same, pointing this way. I would say they're the same. Not because the molecular formulas are similar, but because the electronegativity of oxygen is much greater than carbon. And I would say the electronegativity of oxygen is also much greater than sulfur. But maybe because this is a double bond, this wouldn't be exactly straight. It is possible different because the lone pairs on. So there are lone pairs here. Oh, so it wouldn't be the same. It wouldn't be the same because this is rigid. This is going to be, we already know that we've beaten this to death. this would be 180 degrees. This is a straight line. But this wouldn't be, because it would have that kind of like cloud of the two lone pairs. Then it would have this oxygen here, which would probably have a negative charge, right? Because where else would that go? And then it would be a double bonded oxygen. Okay, so it wouldn't be the same. So it would be different. So A and B are out. They're different because the lone pairs of electrons on the S atom make the negative end of a dipole, and different because S has a greater number of electron domains, regions of electron density surrounding it than C does. Yeah, I mean, I guess that's it. Regions of electron density, is if that's what you want to call them. Different because the lone pair of electrons on the S atom make it a negative end of dipole. I definitely think it's a D. Because this is what they're talking about. An electron domain. It's a region of electron density right here. Because, when you have those two lone pairs, they're not just sitting there. They're just like, they're moving so fast. So it looks like a blur. So I guess that would be called the electron domain, or the region where the electron density is. Okay. Which of the following contains the smallest bond angle? So you would want the most things. This is definitely not the smallest bond angle. Now, this would be equal. This would be, believe this would be 109. And because this one is double bonded, I believe these two would be like 107. And yeah, I believe, here, let's go back really quickly. There are 4, it'd be 109. So I think that's the smallest. And unless there's an electron cloud and it's bent, and I don't think any of them are bent, right? So there's no electron cloud here for any of them. Well, I guess there's an electron cloud here. And so this might be bent, right? Because this oxygen is probably here. So I'll pick D. Right, because these two, right, this oxygen actually is probably 107. Okay. Yeah, these are 109. Is it 109 or is it even more? It depends if this is on a plane. I guess if this is on a plane, this wouldn't be 109. This would be 120 each, and then these would be 109. So yeah, so I think that D is the answer. Okay. So let's go back. Let's look at the carbon. Right here, we have, normally they're just pi bonds, right? They're sigma bonds, two carbons that are bonded together. Let's see an example. Yeah, so normally there would be just carbon-carbon sigma bond form, right? And so when it overlaps, that's when there's an sp2 and an sp, and the sp2 they call pi bond. So let's go back. So I would call these sp, right, or sigma bonds. I think sp2 would be pi bonds, if I read that correctly. The hybridization of the carbon atoms in the molecule of ethene would be represented above. So here and above shows a carbon, a hydrogen, so that has a triple bond. So triple bonded carbons would be sp hybridized. And because it's sp hybridized, because there's one sigma bond here. There's one sigma bond, right? The one that looks like this. But there's two pi bonds. So here, there's like one regular bond, and there's two pi bonds. There's two pi bonds, and so that's where we get the 3. So this one would be sp hybridized. And so okay, so this one wouldn't be sp hybridized. Sorry, this one wouldn't be sp. This would be sp3. Sorry, right? And this one sp3 because up here there's 4 sigma bonds. Here, these are all sigma bonds. Sigma bond, sigma bond, sigma bond, sigma bonds. These are all sigma bonds. So this is sp3. This is called sp3. And this is sp because this has one sigma bond and 2 pi bonds. Sorry about that. Okay, whoa. That's a lot of questions. Okay. So a lot of this is just referring to, here, let me put a VSEPR theory. And we can just pull up this image. I believe I gave a copy of this last year. Okay. And so we're just really referring to this right here. Okay, so which of the following molecules shows 3 sigma bonds and 2 pi bonds? So 3 sigma bonds and 2 pi bonds would be something that has 3 bonds, so 3 sigma bonds, right? And then 2 pi bonds, right? So this would be, let's see. No lone pairs. And then so if you have 3 sigma bonds and 2 pi bonds, then you would let me see the examples here. HCN, ASO3. So you would want something that has a triple bond, right? And so this does not have a triple bond, but this might have a triple bond. It's a carbon, but then there's a hydrogen here. Then it'd be triple bonded, and then a carbon, and then a hydrogen here. So A could be the answer. It can't be CO2. Because 2 pi bonds kind of give it away that it's sp3. And so I would say it's A. Which one has the largest dipole moment? This one for sure, because it's the strongest electronegative thing. And here it cancels out. There would be nothing here because these two would cancel. Then F and F would cancel out. This one is the most electronegative, right? This one would be this answer. Which one has a pyramidal shape? I wonder if this one has the thing. So a pyramidal shape would be trigonal bipyramidal and trigonal. Okay, let's go back then. Which one is considered? I think pyramidal is 4 of the same thing. kind of, or similar bonds. Here we go. Pyramidal. Square pyramidal is not the same. There's two things that are similar. There's trigonal pyramidal and trigonal planar. Okay, so it would be this. So it has to be something. There's a lone pair here, and then there's three other things that are bonded to it. So it definitely can't be this. It can't be this. It can't be this. So now it needs to have three things bonded. So it can't be this either, and I'll tell you why. Boron, if you look at a periodic table, boron has 5 valence electrons total. And when you go and you try to draw that, it ends up being 3. Let's say this is boron, right? That was the worst place to draw it, right? So here's boron. It's 1, 2, 3, and then the 3 hydrogens come, and then there's no lone pairs. So this can't be it. Nitrogen here has 7, so it has 1, 2, 3, 4, 5. The 3 hydrogens come along, and that's how you get pyramidal, because you get this electron kind of cloud, and then you get 1, 2, 3, and that's pyramidal. So this answer is A. Which of the following molecules contains polar covalent bonds but is a non-polar molecule? Okay, has polar, well, I think almost all of these have polar covalent bonds. But the molecule overall, so it has to be something that cancels out, right? So this one is probably it, because this is carbon, chlorine, 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 right? So there's a dipole moment going this way, because this is very electronegative, right? Not negative, but electronegative, right? And so this one is electronegative, and then this one is electronegative, and they're all equal, right? Because it's the same atom, and so they all cancel out. So it's non-polar molecule, but it has 4 different polar covalent bonds. Okay, getting a little fatigued here. There's a lot of pages left. Which of the following arranges the molecules N2, O2, and F2 in order of their bond enthalpies from least to greatest? So, which of the following arranges in bond enthalpy? So wait, what first is what is bond enthalpy? So bond enthalpy is how the bonds are gonna actually require for it to break. What is the strength of the bond? And here they talked about here the energies and the strengths of the bond, and they talked about how a triple bond would be stronger, and they talked about how different bonds have different strengths. Where to go? Here. Not this far ahead. Not this far back. Where'd it go? We definitely sat here and read about it. What? This is like VSEPR. Okay. But they didn't talk about bond strength here. I think after here we go, bond energies. So here, as if we look at a periodic table, right? F, O, and N. So F is is bigger, right? But its bond energies are less. And so here what we're talking about, and then oxygen and nitrogen, right? But here it talks about bond energies will increase as we move from as we move from single bonds, double bonds to triple bonds. And here we talk about the radii, the size. Here the size here. Okay, so here as the size increases, the bond length will also increase. So that's what we're seeing. Bond length increases. Okay. So, if we go back to the original question, so that means here we see a trend of fluorine being the smallest too. So if we go back, fluorine should be the smallest, so it would be A. So that makes sense because fluorine would be because it's from least to greatest. So fluorine would be first, and that's the only one there that has fluorine as the first. And so, just to make sure my answer is right, nitrogen should be the greatest. Then, and nitrogen is the greatest here, so this is the only right answer. Pi bonding occurs in each of the following except pi bonding usually happens when there are a double bond occurring. And there's a double bond that occurs here with the CO. There's a double bond that occurs here between CC. Here we have CN. I believe this might even be a triple bond. Here we have possibly some double bonding here. But where we don't have any double bonding is here. There's no pi bonding happening here, just sigma bonding. Which of the following has the shortest bond length? Okay, so if we go back here, bond angles, bond energy, and bond length, it'll decrease as we have triple bonds, and it'll increase as the atomic radius increases. So one of those factors should come and reveal to us what we are looking for. Okay, so which one has the shortest bond length? So these are all double bonded. Okay, so whichever one, what did they say? As we increase the size, that also increases the bond length. And so the question is asking, which one is the shortest? Oh, it's the smallest one in size then. That was very easy. That's A. Yeah, all of these are bigger than nitrogen. Okay. According to the VSEPR model, the progressive decrease in the bond angles in the series of CH4, NH3, and H2O is accounted by the electronegativity of the central atom. It's usually because of increased number of unshared pairs of electrons. If there's like an electron cloud, right? If there's an electron cloud, then that has a stronger, repulsion, and so that decreases the bond angles. Okay. Let's look at these. Okay. Which of the following is a non-polar molecule that has polar bonds? This is not polar because they're the same thing, right? Here, it cancels out whatever polarity there was. It's carbon with oxygen on one side, oxygen. Since they're equal, this cancels out. Is a non-polar molecule. It means overall it's not. Oh, so this would be the answer. Wait. So this would be polar, has polar bonds. So this carbon and oxygen and carbon and oxygen. So this would be the dipole moment, right? But they cancel out since they're opposite directions of each other. So C would be the answer. I didn't read the question clearly. So these are polar bonds, right? This is polar. But overall, this molecule is nonpolar. Which of the molecules represented below contains carbon with sp2 hybridization? So we talked about earlier how sp is a triple bond and sp3 is a single bond, and so sp2 would be a double bond. So which of the following molecules? So this one's talking about a double bond, right? A double bond. And so which one of these is basically asking has a double bond? And I believe it is carbon double bonded to carbon, and this has no, it's definitely not this either, because that would be 1, 2, 3. 1, 2, 3 would make 6, and that's impossible because these are double bonded, so it can't be this one. I don't know how these chlorine would fit in. So it would be carbon double bonded to carbon, and it could fit 1, 2, and 1, 2. So it could be a 1, 2, 3, 4 other things, and I guess this one has 6 other things attached. And this one has 4 other things attached. The answer would be D. Okay, which of the following has zero dipole moment? There's definitely a dipole moment here, I believe. There's a dipole moment here. I believe this S is double bonded to oxygen and then double bonded to oxygen and then has something here. So it's 1, 2, 3, 4, 5, 6. I believe this has no, because I think it's P, and then it's equally F, right? Because I believe P can hold exactly 5 because, let's check the periodic table, P has is in group 15, so it has 5 valence electrons. So it shares 1 and 1 and 1 and 1 and 1 for 5, and as the 5 come, they're equal distance away from each other, and it cancels out the dipole moment. Which of the following species is not planar? Probably PCl3, because P, right, like we just talked about before, would have this electron cloud, and the Cl3 would be like this, Cl, Cl, Cl. Okay, last question. The Bf3 molecule is nonpolar, therefore the NF3 molecule is polar, which the following accounts for the difference in polarity. Well, remember, Bf3, if you look at the periodic table, Bf3 has 3, after you subtract the 2, has 3 valence electrons. NF3 has 5 valence electrons. Which of the following statements accounts for the difference in polarity for the two molecules? So let's see. In NF3, each F is joined to the end with multiple bonds. That's not true. NF bonds are polar, whereas BF bonds are non-polar. That's not true. They're all polar because F is very electronegative. NF3 is ionic, and BF3 is, that's not true. D has to be the right answer. Let's see what it says. Unlike BF3, NF3 has a planar, non-planar geometry, which is true, which is what the question is asking, due to an unshared pair of electrons. Now that's the truth, because N is 1, 2. This is the unpaired share. This is like the electron cloud. And there's 1, 2, 3 that it shares with the F's. And so there we go. 1, 2, 3. And so that's why this is not planar, because of this unshared pair of electrons. And so this is D.